Hello everybody and welcome back to RSW Tutoring. Today we will be taking a look at sigma notation, summations, and an intro to series. So let's begin with the fact of what's the difference between a sequence and a series? Well, let's just take this example, 2, 4, 6, 8, and let's just say this goes on and on and on. It's an infinite sequence. So what do we have to do to this sequence to make it a series? It's very simple, guys. All you have to do is just add these terms together. We just add them, and the ellipsis stays the same. Now, this is referred to as a series when we add the consecutive terms of a sequence, right? When the terms of a sequence are added together. And a finite series has a fixed number of terms, an infinite series continues indefinitely, as we've said before. And now, a series can be written in something called a sigma notation. And sigma is often represented by the Greek or the 18th Greek letter, and this means sum in mathematics. So sum, why we're adding the terms together. Now, there's a specific type of notation in math that we use to represent a series, right? And that would be the sigma with the lower limit, which could be any number, let's just say x, and the upper limit of y. And then in the actual sigma itself, we put our general term, okay? So that is the way we express it. I will get into an example to explain how this works. But the general thing that you have to understand right now is that our sigma notation works as follows right here. And the difference between a sequence and series, that a sequence is just a set of consecutive terms that follow a particular pattern. And then a series is actually taking these terms and adding them together to get a finite or an infinite sum. Depends. Now, let me give you or lay it out in an example. Let's just say we wanted to find, let's just say we had the general term 3n minus 2, okay? And hypothetically speaking, we wanted to find, let's just say, from the lower limit of 1, okay? So we wanted to find if we plugged in the terms from 1 to 3, let's just say, okay? If we wanted to find, what would be the sum? Now, bear with me here for a second. We have to substitute in the lower limit all the way up to the upper limit, every number in between, and then add those numbers together. So what would that look like? Well, that would look like 3 times 1, right, minus 2, plus 3 times 2 minus 2, and then plus 3 times 3 minus 2. And then what does that give us? Let's do some mental math. So this would be 1 plus 4 plus 7, and that would end up giving us 12. So do you see what's happening, guys? All we have to do is just substitute in the numbers into the formula. So whether that's 1, whether that's 2, all the way up until the upper limit, and add all of those terms together. It's really, really not that hard. Let's take a look at a different example now to consolidate our knowledge. How do we go about finding, let's just say, the next terms, right? As we did right there, and finding the actual sum. So let's just say I had a sigma notation, right? And let's just say we're going from n equals 1 to the upper limit of 4, and our equation is going to be negative 1 to the n multiplied by n plus 1. So how would I go about doing this? Well, extremely simple. Again, all we have to do is just substitute in all of the corresponding terms from the lowest to the upper limit and then add them together. So this would be negative 1 to the 1 multiplied by 1 plus 1 plus negative 1 to the 2 multiplied by 2 plus 1 and then plus negative 1 to the 3 multiplied by 3 plus 1. And then our last thing that we have to do is negative 1 to the 4th multiplied by 4 plus 1. Let me get my calculator and I will be back with the answer. So for those of you that got 2, you are 100% correct. That is the right answer, and you are on the right path if you did indeed get this solution. Now, let's take a look at a different example, okay? Let's just say we wanted to find the sigma from n equals 2, right, to 6 of 4n minus 3. Again, what do we do, guys? We just substitute in the numbers. So it would be 4 times 2 minus 3 plus 4 times 3 minus 3, and then plus 4 times 4 minus 3, and then plus 4 times 5 minus 3, and then plus 4 times 6 minus 3, okay? And once again, I will get my calculator and plug in the numbers. The final answer should be 65. So for those of you who got 65, good job. And guys, always remember, if you think you know how to do it, pause the video, try it, and that's the only way that you're going to get better at these skills. So let's just take off this example and do one last one. And this one would be from n equals 1 to 3, right? A sigma notation. And the expression would be n multiplied by n plus 1 equals a certain number, or sum. So let's do the math here. So this would be equal to, right? It would be equal to 1 multiplied by 1 plus 1 plus 2 multiplied by 2 plus 1 plus 3 multiplied by 3 plus 1. So again, how to do the math? 2 plus 6 plus 12, right? And that would give us 20. So if you got 20, that is the correct answer. Now, let us move on to actually finding the sigma notation from a given series. Now, this is where it tends to get a bit trickier, but we must deal with it and accommodate accordingly. Now, I remind you guys, before we even start these examples, when you're looking at that series, it's not much different than a sequence. We're just looking at it in a difference of pluses or commas or whatever it is, but we're still trying to find the same general term. It's the exact same concept, and I'll show you what I mean. So let's just say we had this series 4 plus 16 plus 64 plus 256, and let's make this, why not? Let's make this an infinite series, okay? So how do we write this in sigma notation? Well, again, if we just ignored the pluses, right, and substituted them in with commas, what would our geometric series be? Because we're multiplying by 4, correct? But what we're also doing is we're simply putting 4 to the power of the term number, if you notice. We're just putting 4 to the power of 1 equals 4, 4 to the power of 2 equals 16, 4 to the power of 3 equals 64, etc. So how do we write our sequence? Well, we write it as n equals the bottom limit, right? The bottom limit would be n equals 1 because that's our first term number, and the top limit would be infinity. And then our actual general term would be 4 to the power of n. And there you have it. That's our sigma notation. Easy, very easy. Now, obviously, granted that when we have an infinity as the upper limit of our expression, in any case whatsoever, that would mean that we would have an infinite sum. So our answer would also be infinity. Now, let's take a look at this example. 3 over 4, okay, plus 4 over 5 plus 5 over 6. Let's just keep that finite. Now, how would we go about writing this? Well, just because in our previous examples we always started n at 1, that does not mean anything. When we put sigma notation, guys, it's important to accommodate according to the question. And if the question starts at a certain number, for example, it starts at 3, or it starts at 7, or it starts at 2 million, it does not matter. But if we can make it work, then that means we are on the right track. So if we said here, okay, if we hypothetically said that the sigma, the lower limit is 3, okay, and the upper limit is 5, why would that make sense? Well, that would make sense because the first term here is 3 and the last term here is 5. Then again, we can also start at 4 and end at 6, but that would be much more difficult. Why? Because our denominator can be listed as a number that's above the term number, for example. I'll show you what I mean. So our general term for this one, guys, would be if our term number is 3, then it would be n over n plus 1. And that is our sigma notation because our denominator is increasing by 1 more than what the numerator is. And this type of question we also went through in our previous video. So if you would like, go check that out. Let's do another example here. Let's do -1 plus 1 over 2 minus 1 over 3 plus 1 over 4, right? And then minus, and then let's just make this a finite sequence. And we use an ellipsis also to represent a finite sequence if it's in this scenario like I'm showing it right now. So it will end at 1 over 100. So what do you guys think? Pause the video, try it, and we'll get into the answer shortly. So this notion of the rotating 1, positive, negative, etc., we covered in our arithmetic and geometric sequences video, but I will explain it one more time. Now, depending on whether these negatives are on the odd or even rotation, you have to write it differently. And what I mean by differently is we can write it as a power, n to n minus 1, n plus 1, or leave it as n. And I'll show you what I mean. So if we would write our sigma notation right now, we see that at the top, the numerator is always 1, so that is not going to change. So if we sort that out, then we should be totally fine. But what we do see is that the denominator corresponds to the term number, right? So our n would be 1, right? And our upper limit would be 100. And our general term sequence, guys, if it makes sense, is simply just -1, right? It's simply just -1 to the nth power, because we're dealing with the negative on the odd terms, right? Because that's why we preserve the negative. But if it was on the even terms, for example, this 1/2 over here that we have, that's term number 2. And when we substitute it in the actual expression, right, the negative cancels out to give us a positive. And then all that's left to do is just multiply that by 1 over n, because that's the term number. Simple. That is the answer. Now, let us take a look at our last two challenge questions, I would say. These are the hardest type of questions that you could possibly get. So let's take a look at this one. 5 plus 10, right? Plus 17 plus 26 plus, and let's just call this infinity. Now, looking at it, we're adding 5, we're adding 7, right? We're adding 5, we're adding 7, and then we're adding 9. So it seems like we're just moving through by consecutive odd terms, right? But that will not work in our sigma sequence. Now, it's not arithmetic, nor is it geometric, and it's definitely neither. But when you have these neither sequences, I highly recommend you writing the term numbers under the sequence terms. So in this case, it would be 1, 2, 3, 4. Now, I know this is extremely difficult to spot, but once you get used to it, it kind of feels natural. So what you have to do is, if you see 5 here, okay? 3 here, 10 here, 4, and 6, and 17. When I look at this, right, I tend to create these arrows and diagonal relationships. If you saw my last one on recursive sequences, you know. But I tend to create these diagonal relationships to get the next term. So for example, I know that if I square 2 and add 1, I get 5. And if I square 3, right, if I square 3, so 3 squared plus 1, 2 squared plus 1, I get these terms. So I have a general term now. I have something to work with. That's the idea you want to get to. So how do we write it as a sigma? Well, if I'm going to start at 2, and that's my first term, right, I'm going to put that as my lower limit because I have nothing precedes 1, right? So I'm going to put that as my lower limit, n equals 2, and I'm going to put my upper limit as, well, infinity. We don't end this series. And then all I have to do is just put n squared plus 1. Simple as that. Very easy. Very simple. And yeah, that's pretty much it, guys. So let me take a look at this last challenging example. This one is going to be a little bit more overwhelming, but it's the same thing. Whenever we substitute numbers with letters, we assume that we are dealing with the same material whatsoever, and that's something we learned since a long time ago. So 81 m8, and then plus 100 m to the 9. So what are we doing here, guys? Well, what we're doing is clearly we have squares, right? And this thing can be written in a variety of different ways, but I choose to write it as the simplest way, which is starting at a term number of 7 because that's what we're squaring, and then moving on from there. So I'm going to start mine as a let's just say here as a sequence where I begin at 7, right? 7, and then I end off at and then here we should have, yeah, we should have 100. Okay, so yeah, I would start it off at 7 and then I would end it off at 11, right? And then what I would do here is I would square the term, right? 7 squared, 8 squared, 9 squared, 10 squared, right? And then I would put the m to the n minus 1 because here if I have 7, 8, 9, right? 10, and then let me just add one more term here, m to the 10, correct? So if I have from 7 to 11 now, right, these are my term numbers. What I notice here is that the first part, the number or the coefficient of the term, will be a square of the term, but the actual term itself is raised to a power that's 1 less than the term. So I just have to, all those words can be just written down mathematically, right? So all we have to do is just say n squared, correct? Multiplied by m to the n minus 1. And that is our sigma notation. So I hope you guys enjoyed that video. I hope that provided some clarification into your issues on summations and a little bit into series. Do not worry, we will go through an abundance of series questions in the next part of this chapter. So please stay tuned for those. Those will be coming up very shortly, and we will get into a lot of detail in terms of the sequence formulas, the series formulas, and all of the other stuff that comes along with patterning, sequences, and series. So thanks for watching RSW Tutoring, and please leave a comment if you have any feedback whatsoever so we can tailor to your needs as best as possible. Thanks for listening.